Okay, welcome back. So I see question in chat saying, can you explain, give advice on the best way to write out the distinct fractions? As we saw last time, the Egyptians had this peculiar way of writing out fractions. Um, Notably that they wanted to express, say a fraction. I think at the end last time I gave an example, like 2 over 45 was expressed as like 1 over 30 plus 1 over 90, which didn't follow that rule that that you could write any fraction of the form 2 over 2m plus 1 in a particular form. So the question is like what is something, or like how would you figure out what these distinct bases are, right? So the idea is to write this uh, as a unit fraction, so or as a sum of some number of unit fractions. Well, so in general, so the thing that you have mentioned here is an example of one of these fractions of the form. So it's 2 over 2m plus 1, so 2 uh, uh, over odd number. So in that case, you have 2 over 9. So I'll do that particular example here in a second. So 2 over 2m plus 1. So this can always be written as a sum of the unit fractions 1 over m plus 1 and 1 over m plus 1 times 2m plus 1. Now, why? Why is this always true? So let's just do the algebra here to check that this is true. So, okay. So if we're going to do this algebra here, what I'm going to do is I am going to, first of all, I'm adding fractions here, right? So the idea is I get a common denominator so that I can actually add these things. Well, this thing has a denominator of m plus 1 times 2m plus 1. So in order to get a common denominator, or I mean an example of a common denominator here that would be easy to do would just to replicate this, right? So to have m plus 1 times 2m plus 1 um, in both denominators. So for instance, here this would become 1 over, if I put m plus 1 times 2m plus 1 here, right, then I can't just do that. That's not going to be right. When I put a plus and I copy this thing here, it's not going to be right. I actually need to have a 2m plus 1 in the numerator as well. Right, that's the idea here. Right, plus 1 over m plus 1 times 2m plus 1. Okay, so then now I have the same denominator. So let's simplify this. I can actually do this sum in the top. So here I have 2m plus 1 plus 1. All right, so that comes from this fraction. Plus 1 over m plus 1 times 2m plus 1. Okay. So then in this numerator, I have 2m plus 1 plus 1. So that is 2m plus 2 over m plus 1 times 2m plus 1. Okay. All right. So then what now? Well, 2m plus 2, I can factor out a 2 here. Right? So this is 2 times m plus 1 over m plus 1 times 2m plus 1. And now I have this common factor of m plus 1 in the numerator and denominator. And what I'm left with is 2 over 2m plus 1, which is indeed the fraction that I claimed this thing was. So forget that I said that this was the case. If we just began with this fraction, we see, this is 2 over 2m plus 1. Okay. Now, there's a couple of questions here. One, why would you have thought to do this? Well, basically, this is a trial and error thing. Before a rigorous development of algebra, this is something that would have been noticed through actually doing a bunch of computations. So, for instance, in the example that you use, the 2/9, for instance, so if we're going to say this is 2/9, and we want to use this pattern, right, to write 2/9 as a sum of unit fractions. So 2 is in our numerator, yep, 2m plus 1. Well, if 2m plus 1 is equal to 9, what does m have to be? So m has to be 4, right? So this is m is equal to 4. So if m is equal to 4 here, this would be a sum. This would be 1 over 4 plus 1, so that's 1 over 5, plus, if m is equal to 4, this would be 1 over 5 times 9, so this would be 1 over 45. Would be an example of writing 2/9 in this way. Okay. So now, you might say, well, okay, that is just, for this particular example of 2/9, that's what you do. But, like, what do you do in general, right? So this is, by the end of class today, I'll talk about, where I'm going to talk about a couple of things and where it ties in with this discussion. But where this is going is, notice that this is actually something that, so first of all, right, we saw before, like, this is not the only way that we could do this. So let's start again. I'll try to do it right here just so that I have all this on one sheet. So 2/3. Now, what's funny is that 2/3 is one of the fractions that the Egyptians apparently were okay to leave like this. And that may be because it was a simple enough, it was like the simplest non-unit fraction. In the Egyptians' mind, this was considered the simplest non-unit fraction. And so 2/3 was actually something that they would occasionally actually write 2/3 not as a sum of unit fractions. But of course, as I said last time, even sometimes they would write this as a sum of unit fractions. So one way of writing this as sum of unit fractions is, well, 1/2 plus 1/6. Okay. Well, once you know this, there is, of course, a way of writing 2/9 in a way that's different than this. So 2/9 could also be expressed as, so once you have 2/3 is, say, 1/2 plus 1/6, how do I come up with another way of writing 2/9? Well, I can just divide this by 3, right? Divide this by 3, or as we know, multiply by 1/3. So if I'm dividing 2/3 by 3, I get 2/9 here, but then I'm dividing the right-hand side by 3, and what do I get? I would get 1/6 plus 1/18. Right? So this is another way of doing it. Now, what does this method have as an advantage over, trying to come up with some general pattern like this? Well, what is nice about this is, notice that me coming up with this way of writing 2/9 depended on me knowing a decomposition of 2/3. And really what it used was the fact that 9 is 3 times 3, right? Okay. So similarly, right, if I knew a decomposition for, say, 4 over, you know, 4 over 35, right, then would I also know a decomposition for, say, 4 over 105? So if I knew a decomposition for 4 over 35, would I also know one for 4 over 105? Yes, because 4 over 105 is, of course, just 4 over 35 times 3, right? Which, of course, allows me to take this decomposition that I got from 4 over 35 and divide by 3, right? That is, multiply the denominators of all those by 3, and I would get a decomposition that way. And so, what this method tells me is that being able to factor numbers into their divisors has something to do, right, with being able to write these. So if I know these decompositions for denominators that are prime, right, then I can build fractions that are more complicated, right, where the denominators are composite, that are not prime, that are, products of prime numbers. So that's where this is headed. So maybe I'll say that before moving on. So this means that coming up with these unit fractions for a general A over B has something to do with being able to factor B. Of course, this is not the only way as noticing that pattern. Of course, that pattern involves this as well, but this gives us an easy way of coming up with some of these fractions if we know decompositions for the similar fractions where b, or for factors of b, I should say. Okay. All right. So what I wanted to mention before getting into this, the notions of factoring, what I wanted to say is the following. So as an aside, remember, right, here was what the Egyptian numbering system would look like. So this was a base 10 system. So this was 10 and 2, right? That was 12. So this was 2 10s and 4 1s, so 24. And this was 48 because it's 4 10s and 8 1s. And this is 9 10s and 6 1s, right? So it's a base 10 system. In fact, even though the Egyptian language is from a different language group than, say, Indo-European languages, which is what English is a part of, it still uses base 10. So Egyptians used a base 10 numbering system. So the Indo-European languages use, so Indo-European languages also use base 10. Well, not just use, they still do. So Indo-European languages, all of the languages of Europe except a tiny few, are Indo-European. So, most of the languages that you're familiar with, like English, Dutch, Spanish, French, Russian, those are all Indo-European languages. There are a few European languages that are not that are not part of the Indo-European family. So if you know some examples of those, there's two big ones that are exceptions, and then there's a couple lesser known ones. But if you know examples of those, you can feel free to list them in the chat. I'll mention them again here in a little bit, but it's interesting to note these kind of things. Linguistics is very interesting. Anyway, so Egyptian is not Indo-European. Egyptian is I think it's Hamido-Semitic. But it used a base 10 numbering system as well. So there are some African languages, I think, use scale of 5, so it's base 5 basically. And of course, we can use any base. So generally, we can discuss a base B number system. So let B be any base. So B is an integer greater than 1. Positive integer, obviously, because it's greater than 1. So let b greater than 1 be an integer. Then we can express any number. So if a is any natural number, so a natural number is a positive integer. Then a can be expressed in base b in the following way. So a is a naught plus a1b plus a2b squared, and so on, all the way to a sub n b to the n. Okay, where each of these a sub i's is greater than or equal to 0, so they can be 0. Okay, so they're greater than or equal to 0, but they're strictly less than b. Okay, and this is true for all I between here, I'll write it like this, for all I between 1 and n. Now, 0 and n, since we're starting with our subscript at 0 here. Now, I wrote it this way as an ascending thing, but of course, the way you've actually, the way that you actually see this more often is written in the other way. The reason for that, if you haven't noticed yet, is that what are these a sub i's? Right, what are these things? So written like this, it looks confusing, right, as to what's going on. So let's see some examples of this. Okay, so what this is called the base B expansion for A. So this is the base B expansion for A. Okay, that is what I've written here. Okay, so to see what this thing actually is, let's consider an example. So let's consider the example of, say, let B equal to 10. Okay, so let B equal to 10, and let A be, let's say A is 5,237. Okay, so B is 10, A is 5,237. Okay, so I want to write 5,237 in the following form. So I want to write 5,237, that's my A, in the form A sub n. Well, what is n here, right? Well, I have to think, what are these things actually supposed to be? These are supposed to be powers of b here, right? So before I slap a sub n here, actually, I'm going to go ahead and write this. Okay, so this is the form I'm supposed to write this thing in. Okay, now let's actually think about what's going on here. B is 10, and I'm starting with a naught times nothing, but this a naught times 1, this is really a b to the 0 here, right? Anything to the 0th power is 1. Okay, so that's really a b to the 0 here. Then there's b to the first, b to the second, and so on. Thinking about it like that, now you see why I wrote it in ascending order. I'm going to write it backwards here. Well, so I would have a plus a naught times 1, b to the 0, plus a1 times b, which is 10, right, times 10, plus a2 times b squared, which is 10 squared, which is 100, plus a3 times b cubed, which is 1,000, plus a sub 4 times b to the 4th, which is 10,000. Okay, now you see what it is that's going on here, right? I have 5,237 written in this form. Okay, what is the issue here? What does a sub 4 have to be? Well, I'd have a sub 4 times 10,000. Of course, these a sub i's have to be between 0 and 10. And they're strictly less than 10. Okay. So then if this were 1, this would be 10,000 plus some stuff. It clearly can't be 1 because 5,237 is less than 10,000. So a sub 4 has to be 0. In fact, a sub 5 has to be 0, and all of the bigger, right, in a sub 4 and larger subscripts, they all have to be 0. And so only a sub 3, a sub 2, a sub 1, and a sub 0 could be anything other than 0. And so what this looks like is, so that's 0. And all the bigger terms would be 0 here too. So this would be a sub 3 times 1,000 plus a sub 2 times 100 plus a sub 1 times 10 plus a naught. So 5,237, it's something times 1,000 plus something else times 100 plus something else times 10 plus something else times 1. What is this? Well, this is 5 times 1,000 plus 2 times 100 plus 3 times 10 plus 7. Well, what do you know, right? That's just the digits of this in base 10, right? So the a sub I are the base B digits. Oh, I'm a little bit off the screen. Why do they have to be 0? So the reason they have to be 0 is because if a sub 4 was 1, then I would be adding 10,000 here, which is too big because my number is only 5,237. Right? If a sub 4 were equal to 1, this would be 10,000, so this single place would be bigger than the rest of these combined. Right? And that's no good. So these are the base B digits. Yeah, someone else pointed out this is these are the digits for each place. Okay, so we're familiar with base 10. We are writing this in base 10, so we know that this is easy for us to describe because it's just the digits that we're used to. Okay. And so, yeah, the reason why these have to be strictly less than 10, imagine for a second that an a sub I was 10, right? What issue does that cause? Well, it causes an overflow in the digits place, right? So when a sub I, if a sub I is equal to 10, it actually shifts the digits, right? Because here you would have a sub 1, say, would be 10, and instead of having, no bigger than 10 here, you would have 10 times 10, you'd have 10 squared, which is a value that belongs to this place, not the tens place, right? So the reason why you're resetting here is because of how digits work, right? This is exactly telling you that it doesn't make any sense for a sub I to be 10 or bigger, because if b is 10, the way that you're expressing this is, once you have an a sub I over 10, you're lumping those into the next place, right? Okay. And so let's do a couple more examples to nail this down. So base b, or base 10 we're familiar with. What about say base 5? So here's another example. Let b equal 5, and let a be, say, let's say, let a be like 76. Okay. All right, so let a equals 76. Okay. So, what does a base 5 expansion look like? Okay, so we want to write 76 as, I'm going to write the digits in the other order just for ease here. So this would be a naught times 5 to the 0, right, or times 1, plus a sub 1 times 5 to the first, plus a sub 2 times 5 squared, plus a sub 3 times 5 cubed, and so on. But at this point, 5 cubed is what? 5 cubed is 5 times 5 times 5, so it's 25 times 5, 125. That's already bigger than 76, so that has to be 0, and all the rest of these have to be 0, so really this is only going to have 3 digits, right? And so, rewriting this, of course, this is, so this would be a sub 2 times 5 squared, that's 25, plus a sub 1 times 5, plus a sub 0. So now we have to think, okay, and of course these a's are allowed to be, they can be 0 all the way up to 5, right? Or they can't be 5 or greater. They can only be from 0, 1, 2, 3, or 4, right? It's base 5. The digits can only be 0, 1, 2, 3, and 4. Just like in base 10, the only digits we're allowed are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So 10 total digits were allowed, starting with 0, ending at 9. Here for base 5, the digits we're allowed are 0, 1, 2, 3, and 4. Okay. So, so then how can I express 76 in this way? Well, I just have to think, right? 3 times 25 is 75, and I need a 1 other than that. So the way of writing this would be 3 times 25 plus 0 times 5 plus 1. And so, what is this? 76 in base 10, which I'm not going to use any notation for. If we just write a number, you can assume that it's base 10. This is 301 in base 5. So the way that we read this is 301 in base 5. Now, why did I say 301 instead of 301, right? Well, because 301 is a base 10 thing, right? 300 is saying 300s, and 100 is 10 squared, right? So 301 is bad. That's a bad term to use. This is 301 in base 5. Okay, here's a joke. All right, here's the joke. Okay, this only works in writing because if I read it out, uh, using this proper way of reading this, um, if I read this out, it ruins the joke. Okay, so 100 implies base 10. Yeah, exactly. So when you say 100, we've defined 100 to be 10 times 10, right? 10 squared is what we're calling 100. So yeah, once you say 100, you're spilling the beans that you're using base 10. So here there are this many types of people in the world. Okay. Okay. So there's that many types of people in the world, and here they are enumerated out. Those who understand binary and those who don't. Okay. This is a nice t-shirt slogan, right? It works great in writing, but the second that I actually read this out, it gives it away. Okay. All right. And the reason it gives it away is because if I read this, there are 1-0 types of people in the world, those who understand binary and those who don't. Okay. Because if I say there are 10 types of people in the world, well, then that's base 10. Okay, but there are 1-0 types of people in the world, and really what's being implied here is this is 1-0 base 2. Okay, now what is binary? Binary is base 2, so b is equal to 2. Okay, so b is equal to 2, and in the other cases we started with a number in base 10 and we put it into base b. But in this case we have a number in base b that we want to put into base 10. So what is 1-0 in base 10? So in base, yeah. So what is 1-0 from binary that is base 2 in base 10? Well, this is so 10 sub 2. This is 1 times 2 to the first plus 0 times 2 to the 0. Right. So this is 1 times 2 plus 0, so this is 2 in base 10. So of course that's the joke, right? That this is 1-0 and in binary is just 2. Okay. Now, of course, the Egyptians used binary, right? So the Egyptians were fond of binary. Where did they use it? We've already seen. In their doubling tables, right? So in those doubling multiplication tables, the Egyptians were using binary. They were using the fact that you could write any number in base 2, right? So when you did this, when they did this multiplication by 12, right? So let's go here. When Egyptians wrote out this multiplication and they said, oh, 12 is 4 plus 8, right? What this is saying is that, oh, well, 12 is really 2 squared plus 2 cubed, right? Uh-huh. Now we can rewrite this a little bit. So this is 1 times 2 cubed plus 1 times 2 squared plus 0 times 2 to the first plus 0 times 2 to the 0. Okay. All right. So what is this if I write this in digits in binary? This is 1, 1, 0, 0, base 2. So in binary, 12 is 1, 1, 0, 0. Okay. All right. Okay. So let's see. Do you always multiply the leftmost digit by the highest power first? Yes, that's the idea. So that I'm writing it this way in descending order because that's the order we have the digits come in, rather than ascending order. That's how we do. That's how we write the digits. Okay. Um, so binary was used by the Egyptians in these doubling tables. The Chinese used binary, so binary was also used by Chinese mathematicians. So the first example of this was about 1200 BC in something called the Book of Changes, which was like a fortune-telling book. Was a like a divination book that used binary to represent like mystical concepts. Okay. There was another example. I believe this was a Hindu classification of meters in verse about 800 BC. So another example of binary use. Is in Hindu classification of meters in verse. Right. Which might, this notion might have been the first thing that popped in your head when talking about binary, because I mean, even in related things, right? If you're thinking about like musical notes, right? The notion of like quarter notes, eighth notes, and so on. Clearly these are powers of two. So this was 800 BC, roughly. And of course, kind of the most popular place that you have recognized binary from is modern computers, right? Obviously, modern computers use binary frequently. Frequently is a pretty ridiculous way of characterizing it, since binary is the thing that powers computers, because the idea is that one is on, right, and zero is off, right? One is on, so current. Zero is off, which is absence of current, right? Okay. Okay. So there are a couple of applications of this that were actually considered in the following problem. So I can actually show you on the page here. So do we get to learn how to use an abacus? So yeah, using the abacus is now using it if you're talking about like speed abacus training. I don't know if you've seen, basically students using an abacus to do really, really quick computations using just, a very large multiplications, division of very large numbers using abacus. That's something that requires, that's a lot of muscle memory. But yeah, I mean, the idea behind the abacus is exactly a base, our base 10 system, and quickly manipulating the beads, right, which are representing the changes in the digit places, right, when you do these computations. So, I mean, the standard algorithm that is taught, to elementary school students for all these operations takes advantage of base 10. Now, Is base 10 like the best? Where did base 10 come from? Obviously, the most reasonable explanation is that base 10 arose in so many different languages because of people counting, with their hands. Of course, you could say, well, what if they only counted, with one hand, right? Base 5 seems reasonable there. From a mathematical perspective, there are reasons why having a prime number as your base is actually nicer in some sense. One of the things I think that blows a lot of people's minds when it comes to thinking about this is, why are certain things easy in say, multiplication, right? So, like, why is it easy to multiply by 10? It's not that 10 is just some nice number that's easy to multiply by. That's not at all true. In fact, the reason 10 is easy to multiply by is because we have a base 10 system. Because we have a base 10 system, going back to our base b expansion, in our base 10 system, right, if b is 10, if I multiply this number, so I have this base b expansion for this number a, and I multiply the whole number by 10, or by another copy of b, what happens? Well, now a naught is multiplying b, a1 is multiplying b times b, so b squared, a2 is multiplying b squared times b, or b cubed, and so on. So what did I just do? Well, I just shifted my digits, right? A naught is now no longer the digit associated with the ones place. It's the digit associated with the tens place, because I've multiplied by 10. Similarly, a1 is, a sub 1 is no longer the digit associated to the tens place. It's now the digit associated to the hundreds place, and so on. So what I've done is, now I have a 0 in the ones place, and I've shifted all the other digits to the left. Right? That's exactly what happens when you multiply by 10. But it's not because 10 is some magical number that causes that. It's because we use base 10. That's why. So if we used base 5, multiplying by 10 wouldn't do that. Multiplying by 5 would do that, right? So multiplying by 5 would be the easy multiplication to do. If we used a base 7 system, multiplying by 7 would be the easy thing to do. If you use a base 11 system, right, then multiplying by 10 isn't easy in base 11, not at all, right? It's multiplying by 11 that's easy. Okay, so a lot of these things that that you maybe associate to the numbers themselves, it's not that, it's just that we use a base 10 system. These divisibility rules, right? This fact that, divisibility by 9, right, has these weird properties, right, to check divisibility by 9, or this fact that, like the sum of the digits, right, the sum of the digits in base 10 being related to multiplication by 9, or whether or not it's a multiple of 9, that purely, 9 is not a magic number in that sense, not at all. 9 is 1 less than 10. That's why the divisibility rule for 9 is the way that it is. In base 11, it is the number 10 that has that divisibility rule. Okay, so a lot of the things that maybe you took for granted as some like ironclad rule that was like true, it was like inherent to the number itself, has nothing to do with the number itself. It's actually the number. It's the system that we're using to express the number. It has nothing to do with the number itself. Okay, so here's some examples of applications of the base B expansion. So that's a little, there we go. So the 6-weight problem is a great example here. Here we go. So yeah, a balance is a weighing apparatus with a central pivot, beam, 2 scales, and set of counterweights that are placed on one of the scales. Suppose we have some flour and we want to be able to put it into bags weighing anywhere from 1 to 63 kilograms. How can this be done using just 6 counterweights? Okay, so we want to be able to do this just using basically 6 denominations of weights. And the answer is use weights of 1, 2, 4, 8, 16, and 32. This will allow you to weigh any integral load from 1 to 63, 63 itself being able to be expressed as 32 plus 16 plus 8 plus 4 plus 2 plus 1. This is me expressing 63 in base 2, right? Only using this many digits, so I would need 6 digits here, right? So in binary, 63 is 11111, right? Okay. So the 4-weight problem, this time, suppose we're allowed to put weights on either scale. How can we weigh bags under 42 kilograms using only 4 weights? And so the answer here is choose weights of 1, 3, 9, and 27. All right, since any integer a can be written uniquely in the form base 3 expansion, where these a sub 1s are -1, 0, or 1. Okay. So this is another way of solving a problem like this. So here your digits, your allowed digits include -1. Okay. Then there's the Game of Nim. So this is a game played by 2 opponents who take turns removing matches from several piles according to the following rules. So first rule is a player must remove at least 1 match in a turn. Second is a player may remove any number of matches from a single pile in a turn. And the player who removes the last match wins. Find a strategy for always winning this game. So the strategy is express the number of matches in each pile in scale of 2, that is in binary, and write these binary numbers one below the other. If, when it is your turn, you can arrange it so that each column adds up to an even number, then you can do the same in every subsequent turn and you will win the game. So I'm not going to go through an exact example of how this works, but here you can, pause the video and have a look at this. So this is when you, so if you have here, I'll get this on the screen. So let's say you have 3 piles containing 7, 5, and 3 matches. So then putting 7, 5, and 3 into binary, here's your list, right? So the top row is 7, this is 5, and this is this is 4, 2, and 1, so that's 7. Here's 5, so it's 4 and 1, and here's 3, so it's 2 and 1, right? So there's my 3 piles of matches. Now supposedly the winning strategy was to make it so that each column adds up to an even number. Again, that was your goal, removing matches till you could do that, and then you will win. So this is the approach explaining how this works. And of course it has to do with placing those into binary. Let's see. Oh, it didn't refocus. There we go. Okay. And so it was proper to talk about these scales of notation in this case because number systems are important. They're important because, as it turns out, not every society kind of came up with a number system that was very usable for doing arithmetic, and in many ways it arguably hurt their development, right? So this is a big question that's not at all settled, which is, are the ancient cultures that were, say, really good at certain types of computation, is it because of the number system they used, or did they come up with a maybe more convenient number system because they were already more, had greater aptitude with this sort of computation versus, so like the ancient Greeks, as we'll see, had a numbering system that was not so great, maybe compared to some others. And of course, the Greeks excelled in a lot of things like geometry, and less so they excelled in, say, number theory compared to like ancient Hindu mathematicians, which had in many ways a better numbering system a lot earlier. So, a big question. It's very fun to think about, what role the number system played and whether or not, certain societies were, better or worse at a certain part of math. One thing that's interesting to note before I move on. So although Egyptians would have used this, binary in their doubling tables, the thing is that basically The Egyptians didn't have a symbol for 0, so I should say that. So the Egyptians had no. I didn't mean to quote here. This is supposed to be parentheses. Had no symbol for 0. So they had special symbols for different powers of 10, but no symbol for 0 here. So basically the Egyptians would have looked at this as this and would have essentially stopped rather than viewing it in this way, because the things that were missing, right, the terms that were missing here would have just been ignored, and it would have been viewed as, obvious, right, what's going on, depending on the size of the number in question. Okay. This is I think a good stopping point for today, since I'm a little bit over time already. So we will discuss prime numbers next time, and continue on with discussion of, we'll move a little bit to the east and discuss Sumerian and Babylonian mathematics, which, as I've mentioned, the reason I wanted to talk about number system bases is that it's required to talk about Sumerian and Babylonian mathematics because they use base 60 in a lot of their computations. So, and again, as I mentioned before, this is something that we got from them. So we took this from them when, whenever you are telling time, right? Time is an example of something being measured in base 60. Okay. So there are reasons for that. It's not just that it's just random, but there are also nice reasons. The same good reasons why 60 works well for time is another reason why we kept it around. So anyway, that is it for today. So I will see you all on Monday. Have a good weekend.